Okay, so good morning, everyone. Welcome to lecture 32. And today we will do continuous random variable, but with two random variables. So I'm going to define continuous random variable. So the two continuous random variables, x and y, are called jointly continuous. Okay, so we are talking about two or more random variables. So the PDF is called joint. If there exists a non-negative function fxy, so this is a multivariable now. So it's a two argument is there, and then it's a single output. So multivariable, single valued, such that for any a in R square, so a is a set in R square, we have this. Okay, so for the probability of the pair xy happening in A, okay, it will be given by this. Okay, so the function fxy is called the joint probability density function. That is the PDF of x and y. Here the domain of fxy is R squared. But we may redefine this in the sense that I will take only positive values. Okay, so I will define the range to be set of all xy such that the PDF takes the positive values. So if we indeed choose a to be R square, then we know that this integral, okay, will go from minus infinity to infinity. Okay. So this modified range is something we have also done in the single variable case, where we only consider the values where this PDF is non-zero, because when calculating probabilities, if you integrate, then the places where this takes zero values will be anyway contributing nothing in the integral. Okay. So so what we do have is that, just like in the single variable case, if we integrate it over minus infinity to infinity and minus infinity to infinity, the probability will should turn out to be 1 for this to be a valid PMF. Okay, as a PDF. So for this to be a valid PDF, it must integrate to 1. Okay, so this is just the extension, and since we have the two variable, now we have a double integral. Okay, instead of, so we have to integrate with respect to x as well as y. So let us see some example on this. So let xy be jointly continuous random variable with a joint PDF given by this. Okay, then the question is find the constant c. Okay, we know that the integral of the fxy minus infinity to infinity. Okay, in this case it will boil down to 0 to 1 and 0 to 1 double integral ranges, and then it will I mean the limits. Okay, and then if we integrate this, and then it should equate to 1, and then from there we will solve for c. And then another question could be find the probability that x lies between 0 and half and y lies between 0 and half. So this is the rectangle, this is the rectangle, this one, right? So it's half here and half here. So we have to find what is the probability that of x and y being in this rectangle. Okay, so let us try to quickly solve this. So so solution to this is, let us say a. So the first property, we have to find the constant c, right? So we have to do minus infinity to infinity, minus infinity to infinity, fxy xy dx dy. This is what we have. So this implies and this must be equal to 1, because that's the property of the PDF. So but then the limits also should now change to 0 to 1. X and y are limited to 0 and 1. So this is 0 to 1, and then 0 to 1, and then fxy is x plus cy square. So x plus cy square, and then this is dx dy, and this must be equal to 1. Now it's about integrating this. Okay, so we can do iterated. So if first let us do an integration with respect to this. Okay, so with respect to x first. So we have x square by 2 plus cy square x. That's the integration of this with respect to y. And then we put the value of y, which are the 0 and 1 values. And then we are still left with integrating with dy. So we put dy here. And this is 0 to 1. And this is, so after doing this, so this is like half plus cy square, because the 0 terms will go away. And this is dy. And this is equal to, so all this is equal to 1. Okay, and so this implies half of After integrating this, we get half of this, and then 3cy cube, and then we have 0 to 1. So this is half plus 1 by 3, okay, and just c, okay. So this is equal to 1, and from there, if we solve for c, then this is c is 3 by 2. Okay, so this is the first part, and then if we want to do the second part, so this is b. So in b, what we are supposed to do is find the probability that x lies between 0 to half and y lies between 0 to half, right? And if we look into the previous the formula, this is what we are supposed to do. Okay, so probability of xy being in a, in our case, a is like 0 to half rectangle. So we have to put the limits according to that, and then we have to integrate out. Okay, so that's what we are supposed to do. So let us do it here. So to find probability that 0 less than equal to x less than equal to half, and then we also have 0 less than equal to y less than equal to half. Then this, so we have to put the limits of the integration 0 to half, and here again 0 to half, and then x plus yeah, so what was that? X plus c is 3 by 2 we computed, so x plus 3 by 2 y square. Okay, 3 by 2 y square, and then we put dx dy. Okay, and it's a matter of just doing this. Okay, so you can complete this, right? Okay, now I can define marginal also, right? Just like in the discrete case or in the single variable case, we define marginal. So here also we can define marginal. So instead of the sum, we have now integral. Okay, so so then the marginal of x and y can be computed from the joint PDF as follows. So what do you see here? You take the joint PDF. Okay, you take the joint PDF and then you integrate out the y. It's like summing up the y. Okay, so that's how you get the marginal. If you want to get marginal with respect to x, then you have to integrate out with respect to y. Okay, similarly, if you want to get marginal with respect to y, then put the joint PDF and then integrate out with respect to x. Okay, obviously this will remain a function of y because you did not integrate that, right? So so let x and y be two jointly continuous random variable with joint PDF. So this is the joint PDF. This is the same as before. And find the PDF. These are the marginals that we are asking for. Okay, so this is the marginal. So we are supposed to find the marginal PDF. Okay, so okay, so we are supposed to do integrate out, right? So let us see. So this is the PDF, and then if I want to compute marginal with respect to x, I will integrate it with respect to y. So and then the region of the integration is also given to us. Okay, so for 0 less than equal to x less than equal to 1, this is the range for x. The marginal that we want to get will be integrating out the y. So this is xy, x comma y, dy. So this is now another y range is 0 to 1 to 0, and inside we have x plus cy 3 by 2 y square. Okay, x plus 3 by 2 y square and dy. So if we integrate this out, then we have xy plus half y cube 0 to 1. So this, if we substitute these values, then what we'll have, 1 will be remaining, and okay, and so we are with y, right? So we have to substitute the values of y. So this will be the remaining after evaluation. What we will get is x plus half for 1. Okay, so this implies the marginal is x plus half, 0 less than equal to x less than equal to 1, and 0 otherwise. Okay, similarly we can have for 0 less than equal to y less than equal to 1, we can compute the marginal. So in this case, again, the original definition says minus infinity to infinity, the joint PDF, and then we have to integrate out with respect to dx, right? So this in this case will be 0 to 1 x plus 3 by 2 y square. So that's the PDF dx, and then if we integrate this out, then this will be half x square plus 3 by 2 y square x, 0 to 1. In this case, now we are putting the values of x. Okay, so we're putting the values of x. What will be left out will be 3 by 2 y square plus half. Okay, so that's so to summarize, fyy will be 3 by 2 y square plus half for 0 less than equal to y less than equal to 1 and 0 otherwise. Okay, remember that the remaining part we put 0 otherwise. Okay. Okay, so let us consider. So we have solved both the parts, right? So I mean, not both the parts. Yeah, I mean there were two things to find here that we did. Okay, now let us move to one more, let us say, problem. So this is the joint PDF of the continuous random variable that is given to us, and these are the ranges. So find Rxy and plot it. So Rxy is this this region. Okay, so range set of all xy such that 0 less than equal to y less than equal to x less than equal to 1. Okay, so this is the range of the PDF, and this is something we are supposed to plot, and then find the constant c. Okay, so constant c will be found by integrating out this and equating to 1, and from there we will get the c. Find the marginal. Again, we have to do partial integrations and so on, and then we have to find the probability like this, and then we have to find probability, conditional probability here. Okay, so let us try to quickly solve this. So looking at the joint PDF, this is the joint PDF we have, and then the plot will be this. Okay, so first of all, it helps to draw the line y equals to x, right? And then the places where y will be less than equal to x, right? So pair of x, y such that y is less than equal to x will be the region which is below the diagonal. Okay, and since it has to go up to 1, okay, so here we will stop. Okay, so here we will stop, and then everything which is all the values pair x, y where x is greater than equal to y is this region. Okay, and yeah, so for the moment Rxy is this, and we are. So the first question, let us focus. The first question was the second question was to find the constant c. So let us now do the constant c. So the constant c can be found out by integrating, right? So the b part is like we know that minus infinity to infinity, minus infinity to infinity, fxy, xy, dx, dy. So this is, it boils down to 0 to 1, 0 to 1. That's are the ranges, limits for x and y, and we have dx, dy here, and this is 0 to 1. And then we have put the CDF here, and now we will integrate it first with yeah. So in this case, limits is something we have to be careful about, right? Because this second limit we have to be careful about, because y is like so we have to, for the y part, right, it will go up to x only, right? So that we have to change. Okay, I don't know why this eraser is so big. So if we want to do a y, then y range we put from 0 to x because it's upper bounded by x. And then x, okay, it's fine. Okay, so if we integrate this out, then what do we get, right? So c yeah, so c x3 by c. Okay, so we are integrating the y, right? So first is y, so c x square and then y square by 2, right? Y square by 2, right? So this is the integration, and now we have to put the limit also, right? and then y we integrate it out, the x is remaining. Okay, so this is 0 to 1, and so this is c by 2 x to the 4. Okay, because y, in place of y I put x, say x to the 4 dx. Okay, and okay, so all this is equal to 1. Okay, so let me do that as well. Is equal to 1, is equal to 1. We are supposed to find c. So if we integrate this out further, then we will be left with c x to the 5, c by 2 x to the 5 by 5. That's the integration part. And then we have 0 to 1 for x, and that must be equal to 1. So c by 10, and that is 1, is equal to 1. So this implies c is equal to 10. Okay, so that was the B part. Okay, and then after that, what was the question? So marginals. Okay, so marginals of fxx and fyy. Okay. Shall we do it here or here? Okay, let us do it here. So this is the C part where we are supposed to find the marginals, right? So fxx, so we have to integrate out the y part. So to find the marginal, so the first thing is to know the ranges. So ranges are this 0, 1. So for x, for 0 less than equal to x less than equal to 1, we have fxx, and we integrate out, right? So minus infinity to infinity, fxy, xy. Since I'm computing marginal with respect to x, I will integrate this out with respect to y, right? So I will integrate this out with respect to y. But y, we knew it lies between 0. Okay, sorry. Y lies between 0 and x, right? Because it's bounded by upper bounded by x. And then fxy, so c was found to be cx. Fxy was c. What was that? C x square y, right? Okay, so c was found to be 10. So 10 and then x square y dy, and we are doing this. So this is like y square by 2. So 5x to the 4. Okay, that is like 5x to the 4. That's it. Okay, and for the marginal with respect to y, what we have is now we have to integrate out, right? So minus infinity to infinity, fxy, xy dy, okay, or dy or dx actually, right? We have to integrate it with respect to x now. So this is something you can find out. Okay, so I don't have to do it now completely. It's the same as before. Now to find probability that y less than equal to 1 over what was that probability of? Yeah, y less than equal to x by 2, right? Y less than equal to x by 2. Okay, then it means like we have to integrate this. Now the y will be upper bounded by x by 2, not by x, right? So remember the probability calculations, how we used to do. So we have to do probability that y less than equal to x by 2. So we have to integrate. So x will go from minus infinity to infinity. Well, it will boil down to 0 and 1 eventually. And then y is bounded by x by 2. Okay, so this is fxy, xy, dy dx. Okay, this is the first time doing the dy. Okay, so so this boils down to the x limit is 0 to 1 and y limit is indeed x to 0 to half. So if we put this value, so this tan x square y, x square y dy dx. Okay, so here we have 0 to 1, and then if we integrate this out, right? So it's like y square. The y square is the first thing, right? So y square by 2. Okay, so whatever be the case, okay, so you integrate this out and then you will get the result. after this. Okay, so this will be some number in the eventually. Okay, so first you integrate with y and then with respect to x. So you are familiar with this by now. Okay, so now I can define so-called joint CDF. Okay, so far we have seen PDF and then how to compute probability with PDF. Now I can go ahead and define joint CDF. So joint CDF is defined as usual, no surprise here. It's just that now I have two arguments, x less than equal to x and y less than equal to y. So joint CDF satisfies the following property, just like in the previous cases. These are extension of this in the two variable case. So fxx can be obtained by putting y to be infinity. So the same as the discrete case, fyy can be obtained by putting in place of x infinity. It's like summing up over infinity. Okay, so it's like marginal CDF you can think of now, and this is marginal CDF of x. And then this is also not a surprise. If we put x and y everything, then this is like the whole sample space S. So the probability of the sample space will be 1. And then similarly, these things are creating an empty event. So there the probability will be 0. And similarly, that rectangle law, if you remember from the discrete case, this is the formula that we proved. So what is the probability of computing in a rectangle? Okay, so this rectangle, this is which is given by, let us say, x1 and then x2, and then we are given y1 and then y2. So this range of x1 to x2, y1 to y2 will boil down to this region. So in the continuous case also you can use the same formula like we did in this case. Proof also goes in the same way. If x and y are independent, then we are supposed to have this. So CDF will split into the marginal CDF. So let us do some example on this now in the CDF for the continuous case. So let x and y be two random variable with uniform distribution. So find the joint CDF. Okay, so that's the question here. Okay, so we are given uniform. Okay. We are supposed to find so we have to recall what was the uniform, right? So okay, so I do have a space here as well as here. Okay, so I can try to do it here. So since xy is uniform 0 1, so individually we can write down the CDF of x, so which is 0 for x less than 1, and this is x for 0 less than equal to x less than equal to 1, and this is 1 for x greater than 1. Okay, so this is we know, this is familiar thing. This is what we know already, and similarly fyy is 0 for y less than 0, and this is y for 0 less than equal to y less than equal to 1, and this is 1 for y greater than 1. Okay, so since x and y are independent, so since x and y are independent, we can use that fact. So xy, and this will be the marginal products. Okay, so here this is the marginal product, and then so here like we have to do these cases, right? So we just have to multiply case by case. So if x less than 0 here, okay, so so if both x and y are less than 0, then the product will be 0 anyway. Okay, so this is 0 for x less than 0 and y less than 0, and this is xy when they lie in between 0 and 1, because then it's xy, right? So for 0 less than equal to x less than equal to 1, and 0 less than equal to y less than equal to 1. And similarly, you can find out that it will be y when x is greater than 1 and y is between 0 and 1. Okay, so this is the case when x is greater than 1 and y is between 0 and 1. And we will get this case, x case, when y is greater than 1 and 0 less than equal to x less than equal to 1. And there will be 1 case when x greater than 1 and y greater than 1. Okay, so that was the joint PDF. So here we know that like two uniform distributions are like independent here, and then we could have just used the independent the marginal CDF, and then we could get the joint by just doing the product. Okay, and this is the figure we have for the various regions. We have also plotted the same figure for the discrete case, and this is for the continuous case. So if you are in this region, then you have xy, here you have y, here you have 1, and then so on. Okay, so obviously these are like 3D plots, but they are done in 2D case. Okay, so these things are supposed to be the heights. Okay, so let us now see the relationship between the CDF and PDF. So what was there in the continuous case? In the continuous case, if you remember, it was the derivative of the CDF, right? So, and then another way to write is that the CDF is the integral of this from -infinity to x, right? So this is the relationship that we know from the single variable case, but we want to know what will be the case in the case of. So recall that for the single variable case, this is what we got. So -infinity to infinity, we integrate the PDF, and then to get the PDF from CDF, we differentiate. Similarly, for the two random variable case, it's just the extension of this. So now we have to do also -infinity to y, -infinity to x, and then fxy uv. I choose uv because x and y are taken up in the limits. And here I have the PDF, joint PDF can be obtained by doing partial derivative with respect to y and followed by partial derivative with respect to x. Okay, so in general, this will be same as dy dx as long as the partial derivatives are continuous. So del by del y are continuous, then mixed partial derivatives, mixed partial derivatives are equal, right? So that's the result that we know for multivariable calculus. In that case, you can change this order. All right, so this is the definition we have. Now we are supposed to, if someone gives you a joint PDF, then you know how to compute the joint CDF. And if someone gives you a CDF, then you know how to compute the joint PDF. Now let us see an example on this. So let x and y be two jointly continuous random variable with joint PDF, which is given by this. And then the question is find the CDF of x and y. So obviously to find the CDF, which is fxy, xy, we are going to use the formula that we had before. So it's -infinity to y, -infinity to y, and then the joint we have to put, right? So that's what we are going to do in this example, right? Okay, so let us do this here. Okay, so the first question is. First question itself would be like, because there is a constant c here, so that we would like to get rid of. So to find the constant c, so we have done this before. So to find the constant c, we have to integrate out, right? So, but this is something like we have already, this example was already there before, right? And it was, the constant was 3/2. Okay, so recall the constant was earlier found to be 3/2. Okay, found before. Okay, so this was already done. So and then we are supposed to find the CDF, and the ranges are also okay for us. Okay, so the range of xy is the set of all xy. These are just formalities, right? 0 less than equal to x less than equal to 1, 0 less than equal to y less than equal to 1. Okay. So since this is the range, then the boundary cases we can already like single out. So fxy is going to be 0 when x is less than 0 and y is less than 0, and fxy xy is going to be equal to 1 for x greater than equal to 1 and y greater than equal to 1. So these are the boundary cases we singled out. Now we would like to find the CDF of the remaining region. So to find the CDF of the remaining region, what we have to do, so xy is by definition -infinity to y. Let us say first -infinity to x, so fxy, and we use uv not to mix with yx, and then if we integrate this out, right? So so what are the like so let me first do this. So minus infinity this, and then I will just substitute the PDF value. So PDF value was x plus 3 by 2 y squared. So in place of x and y, we have u and v, right? So u plus 3 by 2 v square and dx dy. Okay. So here, first we integrate, let us say with respect to u. Okay. So if we integrate this with respect to u, then what do we have, right? So this is okay, and y is the PDF was 0 only when PDF was 0 otherwise, right? So it makes sense to actually start from 0 to 0 to y, and then 0 to y x here, and then u plus 3 by 2 v square d. Oh, sorry, it should be du dv here. Okay, so du dv. And yeah, so we integrate this. So if we integrate this with respect to the inner one, so if we integrate this with respect to inner one, then what do we get? Half of u square plus 3 by 2 v square u, right? So v square u, and the limit for this will be 0 to x. Okay, and then the remaining part that is left is dv. And if we integrate this out, then okay, so now we are doing with respect to v. So this will be u square v, and then so on, and yeah, so 0 to yeah, so not this, but so if I integrate this out, so u square v plus 3 by 2 v3 by 3 u 0 y 3 gets cancelled. So half of this. Okay, so after all this, okay, after I did the integration, right, it should have been in x, right? So I should do this, guys, in x, because I substituted the value of x, right? So I did not change back to x. So this is v square. Oh, okay, sorry, I am mixing many things here. Okay, I have done this step, and then I was supposed to do one more, maybe, because here so here, okay, so here first I substitute x, okay, and then what I will get is in terms of x, so half of x square plus 3 by 2 x v square, and then this is like dv, and then after that I integrate it out, then I was supposed to get x square y plus half x y cube is the answer, right? So this is the yeah, so this is the CDF of x and y. Okay, so this is the CDF of x and y, and then yeah, in the other cases also. So what are the other cases left, right? So we have this for x greater than equal to 0 and less than equal to 1. And then you may also like go ahead and do this for the other cases. The other cases are when y is greater than 1, right? So greater than or equal to 1. So these are cases you do it further. So for 0 less than equal to x less than equal to 1 and y greater than equal to 1, so you do the same way integrations, and then for 0 less than equal to y less than equal to 1 and x greater than equal to 1. Okay, so when we say this greater than equal to 1, now the limit that we are supposed to get, okay, it's is the lower bound is 1, right? So if you are substituting the integration, the lower bound will be like 1. Okay, it's like 1 to x. Okay, so I mean, yeah, so for the x it's 1 to x, for y it's like 0 to y. Okay, and then if you do this integration, and then you will get something in hand. Okay, later. So I leave this up to you as an exercise. Okay, so yeah, that was the only thing left for this, right? Okay. So definition of the conditional and conditional CDF. Okay. So in general, what we can write down is the following. So let X be the continuous random variable, and let us say A be an event that satisfies this, where possibly B could be infinity or A could be minus infinity. Okay. So in general, I can write down the PDF from the CDF using this expression. Okay, so that's one way. Like if someone gives me the CDF, and then we are given that X lies between A and B, then I can use this, and similarly, if I have to find, let us say, and moreover, like this is a conditional actually. Okay, so this is like X given A. Okay, so that can be found like this. Okay, and then yeah, okay. Like we may try to prove this. So we may try to prove this actually. So let's try to do that just to see why this is the case, right? So this is the event we are given, and we are putting a conditional on here, right? Okay. So let us try to prove this using, because we know the definition of the conditional, right? So let us try to do this. So let us define an event. Okay, I did not say what is A, right? Oh, okay. I think okay. Let me like rephrase what I have been doing here, right? Okay. So I believe A. What I mean by A is this. Okay, the conditional is on this A. Okay, and X, yeah, X is as usual, and then the condition that is being put is on this event A that I have forgot to define here, and then for that this is the expression I'm going to get. Okay, so let us try to prove this. So let A be that event that was given to us. Okay, and so then by definition, X given A, X is probability that X is less than equal to X given A. Okay, so this is the definition that we know. This is the single variable case now, right? So this is the same thing as saying X less than equal to X given A less than equal to X less than equal to B. Okay, so this is like this, and now this is something we know, right? So this is probability that X less than equal to X, and we have to create the joint, right? And then A less than equal to X less than equal to B, and then we divide this by probability of this guy, which is A. Okay, equality or the strict equality doesn't matter in the continuous case. Okay, and okay, so what do we note? If X is less than A, then it will be 0 anyway, right? So if X is like less than A, the joint, this one won't be satisfied. So this joint probability will be 0 anyway, right? So if X is less than A, then clearly f X given A of X is 0 because probability that X less than equal to X, A less than equal to X less than equal to B is 0, right? So okay, and if A less than equal to X less than equal to B, then let us see what do we have, right? So f X given A X, and then so we carry on from here. So if X is given to be in this, then like the intersection of these sets will be just X between A and B, right? So this is the same thing as A less than equal to X less than equal to B. Okay, in the joint we are supposed to take the intersection, and this is divided by the probability of A that we know, and this probability we know using CDF is given by fx Okay, I'm talking about X here, right? Okay, let's see. Yeah, so since I'm talking about X, and so the intersection will be the, yeah, we have not computed the intersection correctly, right? Because this is a variable here. So the intersection will be defined by the X. Okay, although X is between A and B, X could also be intermediate value. So in that case, it should be bounded by should not be B, but it should be rather X here, right? Okay, be the X here, right? So the intersection of X less than equal to X and A less than equal to X less than equal to B is the lower bound will be given by A and the upper bound will be given by whatever value X took, right? So this is what we have, right? So this is fxx minus fxa. So this is something we know already, how the probability for this is computed by like this. And then, okay, probability of A will be, probability of A is like this, right? So this is nothing but FB. So this is like FB minus FXA, right? So, all right. And what are the other cases? If X is greater than B, then if X happens to be greater than B, then the CDF is going to be 1, right? Because in this case, it's 1. So if it's greater than B, then Fx yeah. So if X is greater than B, then so it will force, if X is greater than B, then it will force each of these to be greater than B, and in that case the PDF is going to be the conditional PDF is going to be 1, right? Okay, so X is equal to 1. So to summarize, we have X given A X, and this is 1 if X greater than B, and then this is Fx X minus Fxa by Fxb minus Fxa, and this is for A less than equal to X less than equal to B, and it is 0 otherwise. Okay, so remember that since this is a continuous random variable, equality or inequalities doesn't matter. Okay, their probabilities are the same. We are dealing with the continuous case now. Okay. Okay, and this was the what do we say? Like this is the CDF, right? Yeah. Okay, there is a mistake here, right? It's capital F. We are computing CDF here. Okay, and to obtain the PDF, I'm just going to differentiate this, right? So other guys are 0 anyway. So differentiation of this is 0, differentiation of this is 0, and then differentiation of this with respect to X. Okay, so d by dx of fxx minus fxa divided by fxb minus fxa. So the variable X is like only here. Okay, and this whole thing is probability of A anyway. Okay, so this is like this, all these things are like, so 1 by probability of A, and then the differentiation of this with respect to this will be d by dx of fxx minus fxa. So this is a constant, so that will go away, and d by dx of fxx is just small fxx probability of A, right? So that's how we get this. Okay, so we have a proof of this, right? Okay, so that's that case. Now, similarly, similar to the discrete case, we can also define conditional expectations and variance, right? So for a random variable X and event A, we have the conditional expectation x given a is given by x, and then you just put the conditional PDF. Okay, the only thing you need is conditional PDF. If you can get hold of this, then expectation is just x times the PDF of whatever random variable you're thinking of. Similarly, we can do this for the function of random variable. Okay, it's just extension of that. Instead of x, you put gx. Okay, so similar to the discrete case, it's just that instead of summation, now I have an integration, right? And this is also we have seen before in the discrete case, and same thing holds in the continuous case. So variance of the conditional is expectation x square of the conditional minus expectation of the conditional squared. Okay, so all this can be established. Okay, so if we see an example in this, so consider the exponential and then answer the following. Find the conditional PDF and CDF of x given x greater than 1, and find the expectation. So once you have the conditional computed, you can use this here in the next question, and then you can also use the previous result to compute the conditional variance, right? So we are given an exponential continuous random variable, and then we are supposed to find these conditionals. Okay, so what do we do, right? So so if we see the definition of this, so these are the conditional expectations, and then the conditional variance we are supposed to, but even before that, what we are supposed to find is the conditional PDF and the CDF of x given x greater than 1. Okay, so let us try to find out. So the first step is the conditional PDF, right? So let A be the event that x is greater than 1. Okay, the conditional part we encode this in we use the notation A here now. So the probability of A again. So the probability of A will be like integral of 1 to infinity. Okay, e to the minus x dx, and this will be just 1 over e. Okay, and yeah, so we are supposed to find this, right? X greater than x given x greater than 1. So this is the PDF we are supposed to find, right? So yeah, so what do we do, right, to find this this conditional PDF, right? So what do we have? Right, so how are we supposed to like find the conditional PDF? So 1 over e is given to us, and so find the conditional PDF and CDF of x given x. So what do we do here? So exponentials are like independent, right, or not? I mean, if I do x and then like x greater than 1, are they going to be independent? So what is this? Yeah. So how should I do this, right? So this would be what? X is equal to x give and then the joint, right? And then x greater than 1. Okay, and then here I have yeah, so probability that x greater than 1. Okay. So so intersection of this, right? So this is so here we need the joint, right? And joint is like here we have the exponential here, right? So it will be like e to the minus x here, right? And then this guy we have computed here. So this is equal to probability that x greater than 1, 1 over e, right? So this is e to the minus x and then plus 1. Okay, the e will get multiplied here. Okay, so this is what we have for the conditional, right? And so conditional, and then we are supposed to find the CDF as well, right? So for x greater than 1, the CDF, we will invoke that formula, right? So x a yeah. So we are supposed to find the conditional CDF, and conditional CDF, we will invoke the formula that we had before, right? So that will be what? So that was fxx minus fx 1, right? So fxx minus fx1 and then divided by the probability of a, right? Okay. So what was that formula? Let us check. Okay. Okay. So this is the conditional we have, right? Fx x given a, we can write this as fx x minus fx a divided by, and given that a is like, yeah, so a is like the lower bound here and b is the upper bound here, right? Okay. So let us see that. Okay, so fxx, this was like fx x minus fx. The lower bound is a, which is 1, and then the conditional, we can just write this PA also here, right? Okay, and so now we are supposed to find fxx now, right? So fxx, how do we find out fxx? Well, fxx should be the integration of this guy, right? So we have, so let us compute fxx, right? So fxx is okay. So fxx must be the integral of the of this guy, right? Oh, okay. Actually, I can compute this. Isn't like I can compute this directly because I have the PDF already available, right? So fxa, okay, x is nothing but the integral of this guy, right? So integral of fx, which and the x greater than 1 was a, okay, and what is and the range is given like 1 to, yeah, because the lower bound is 1 for x, and upper bound we take u arbitrary, right? Okay. Okay, so this is what we have, right? So this is what we have, like we compute the CDF from the PDF by doing this integration. Look, the formula told you minus infinity to x, right? But minus infinity to 0 is not taken here because we have the lower bound on x is 1. So that's why we fall back on 1. And then instead of x, we use u because x is already used here. Okay, so fx given the conditional. Okay, so this formula we have e to the minus x plus 1, right? So 1 u e to the minus x plus 1 dx. Okay, so what is the integral of e to the minus x? Okay, what do you recall? E to the minus x integration is e to the minus x by minus 1, isn't it? Okay, if you recall. Okay, so if we do this integration, then this is like the whole thing here, right? So e to the minus x plus 1, and then like the derivative of this guy, right? So we substitute u here, so e 1 minus 1 plus e to the minus 1 plus 1. Okay, so this comes out to be how much? Okay, so the way to write this would have been the other way, right? If you have write in like x, and then you put u here, and then you get things in u. and then you have his x here, okay, and then you have in u. So that way what you will get as an output will be x, right, which is what we typically looking for. So this is like 1 minus e to the minus x plus 1. Okay, so that is the CDF that we found. Okay, what else was there? So this is done. So now we have to find the conditional expectation, right? So for conditional expectation, what we have, so this is the B part, right? So we have expectation of x given x greater than 1 is, so x is greater than 1 is given. So this is like 1 to infinity. The lower bound is sure. So x, and then what we are supposed to substitute here is x given x greater than 1. The PDF of this conditional, that's what it goes here. Okay. Now this is a matter of just computing, right? So x, and the PDF was, for us, it was known to be minus x plus 1 dx. Okay, that's what we computed before. So e can be taken common. So this is like x e to the minus x dx 1 to infinity. So if we integrate this out, and then by substitution, okay, yeah, so you solve this actually, okay. I think it should be possible to solve this further. Okay, I'm not going to like, you can use the product rule, right, of differentiation of the product, right? You take this as a first function, take this as a second function, first function, and then integration of second minus integral or differentiation of the first and integration of the second, and so on. Okay, so you should be able to compute this and find an answer. Okay, you can. Okay. Okay, so that was the conditional, and then, okay, and then we were also asked to compute the variance, right? And variance will be, we can apply the usual formula of the variance, right? So for the variance part, it's very simple. Okay, so for variance we need the, first of all, x square x greater than 1 part, right? So this is like x square f x given x greater than 1 x dx, right? And the range is like 1 to infinity. So this is like 1 to infinity, and x square e to the minus x plus 1 dx, and then it can be solved further. Okay, so expectation you have found. So overall, now what you will do is that you will substitute it, you will use the formula that x square s greater than 1 minus expectation of x square given x greater than 1 whole squared. Okay, so this is what we computed before, and this is what we have also computed before. We substitute this here, and we get this conditional variance as well. Okay, so okay, so I think it's good to stop here, and then yeah, see you in the next class. And in the next class on Wednesday, you will have a quiz. The first half, 30 minutes, will be the quiz. Okay, we did not agree on suitable time, but so hence we have to do it in the class time. Okay then, so